Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're continuing with our series on writing a ray tracer in C++ using as far as possible only the standard libraries and the SDL2 library so that we can display results in a window. This should be pretty much multi-platform. I'm working in Linux as I do for all of these videos, but if you want to follow along with Windows or any other operating system, that should be possible as well. As long as it supports a modern C++ compiler, you should be able to make it work. So today we're going to continue with our series looking at normal maps. You'll recall from the previous episode we looked at how we could implement a very basic normal map to create just a very simple rough kind of looking texture. We also looked at a little bit of the theory behind normal maps and what normal maps were. Today what I want to talk about specifically is texture-based normal maps, and this is a concept that I've created. I don't know if it's really a standard thing, but it's something that I've done and I think yields quite good results. As we can see with the animation going on behind me, that's the kind of results that we can produce. So what we're talking about here specifically is where the normal map is actually derived from the texture. So we've talked about procedural textures before and how we can create interesting and more natural looking patterns with those. And what I think is quite useful to be able to do is to be able to derive a normal map directly from a procedural texture, just in order to give it more sort of surface detail, more character, and so on. So that's what we're going to be looking at today. Just before we dive into that, I just want to say, as I always do, that if you like this video, please do remember to hit that like button. It really does help with the YouTube algorithm. And if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Thank you very much. Right, let's jump into it and let's have a look at texture-based normal maps. Okay, so starting with the animation that we've seen before, this is a really nice demonstration actually of a normal map. Let's just zoom in to the cube on the right that actually has the normal map applied. So we zoom right in here now to the top surface of the cube, and you can see how the normal map is perturbing the reflection of the yellow sphere and to some extent the blue sphere as well. And this is what we're talking about. So this normal map is derived from the texture. So there's a specific procedural texture that creates the pattern that we see, and the fact that we've zoomed into it here with no loss of detail demonstrates the power of procedural textures, I think, really rather nicely. And you'll notice that the normal map is following the pattern of the texture, and that's because the normal map is derived from the texture. If we scale the amplitude of our normal map down to 0, like so, we can see that the reflection then becomes completely smooth. It's now like a polished mirror-like surface. And if we scale the amplitude of the normal map variations back up, then we can see that we go back to the kind of rough sort of looking texture that we would expect. So we can see that a texture-based normal map can be a very useful thing to create additional surface detail, and you can see it's not only affecting the reflections, it's affecting the shadows and things that are going on there as well. So that's what we're talking about today. We're going to look at the code, how we go about implementing a texture-based normal map so we can create this kind of effect. Just before we jump into the code and actually start looking at how to do that, I just want to show a very simple example that illustrates exactly what it is that we're doing. So in this example we have a plane, and on that plane is a very simple gradient texture that goes in value from 0 on the right hand side to 1 currently on the left hand side, and the arrows indicate the direction of the gradient of that texture. So we're computing the gradient of the texture at each of the points where the arrows begin, and then the arrow points in the direction that the texture is going. In this case, just the gradient, okay? It's a simple gradient, a linear gradient texture. Now, if we rotate the texture through 180 degrees, like so, you can see how this works, right? So as the texture rotates, you can clearly see that from the red and the white moving around, and you can see how the arrows change to follow that, okay? And this is important because this is the concept that we're relying on to actually make texture-based normal maps. So with the gradient like this, if we were to apply that or apply a perturbation to the normal based on this, we would effectively be modeling the plane that you can see here in blue. Okay, so now this blue plane doesn't really exist, but what we want is to somehow perturb the normal of the plane that we do have so that it matches the normal of this blue plane, as that is what would be represented by our gradient. Okay, so let's have a look. This arrow here shows this is the normal of the blue plane, and this arrow shows the normal of our original plane. And what we want to do is to find a way to adjust, as you can see here, the arrow of our original plane to match the arrow of the hypothetical blue plane. And we're going to do that using a technique called numerical differentiation. This is something I've talked about before when I talked about gradient descent methods. I'm not going to go into it in any great detail, and what we're going to do is actually have a look at the maths of that when we come to look at the code, because I think sometimes it's easier to see the maths written out in code rather than looking at the equations and things. So I hope that will be sufficient. So in order to make that work, what we do is we use the numerical differentiation technique to compute the gradient of a texture at every point or at any point in the UV space, and then what we need is a way that we can use that to perturb the surface normal to match the gradient. Okay, so let's just have a look at another example first. So in this case we have a circle wave. Okay, the yellow arrows, as before, show the direction of the gradient, and the purple arrows show the adjusted normals. Okay, so you can see as the animation plays through, see the circular waves are rippling out as we would expect, and we can see the yellow arrows conceptually fit with what we would expect to see for how the gradient direction would vary with that animation, and the purple arrows show how we would perturb the normal based on those gradients. Okay, so we're very simply, all we do to implement a texture-based normal map is we numerically differentiate our texture at the point of interest, and we simply then use that gradient, which would be a two-dimensional vector, to perturb our normal vector in a particular direction. It's really that simple, and it's a very powerful technique I found to create really nice illustrations. And like I say, and I really want to emphasize this caveat, that this is something I've developed myself. I don't know if this is a standard technique. It might be. I'm not really sure, but I've developed it myself, and I think the results are really quite nice, and I think it's something quite interesting and worth talking about. Okay, so that's it for the introduction. Let's jump in and let's have a look at how we can actually implement this into the C++ code for our ray tracer. So I'm here just at the terminal window just to start with, and I just want to show you, if you clone the repository from GitHub, or if you've been diligently following along, you should have something similar to this. If we go into the QB Raytrace subfolder, then you can see we have the QB normals directory that we created in the last video, and we have QB textures. Those are the subdirectories of our code base that we're going to be working on today. If we go into QB normals, here we have normal base that we created before, constant and simple rough that we created in the previous episode, and we also now have texture normal, and this is a class that represents a normal map that is based on a texture, which is what we're talking about today. So I'm going to talk about the code for that and talk about the changes we have to make to our other various bits of code as we go. So let's just go back to the root. There we go. Okay, so to start with, I want to just look at the normal base class that we created in the previous episode, because we have to add a little bit of functionality to that. So starting with normalbase.hpp, the only addition here, with the comment with the 3 stars as before, is the addition of a new function called textureDiff. Okay, this returns a vector, a QB vector double object, and it accepts as input a reference to an input texture, okay, using the STD shared PTR of type texture base, right? And it also accepts as input the UV coordinates. So you can see from that what it's going to do. It's accepting the pointer, a reference to the input texture, and then it's going to use the UV coordinates to evaluate the procedural texture at that point, and it's going to compute the gradient, which is two-dimensional, so it returns a vector. Okay, that is the only change to the HPP file. Let's go and have a look at normalbase.cpp. Okay, normalbase.cpp, and we haven't changed very much here. So we have the compute perturbation method, and we have the perturb normal methods that were functions or methods that we talked about in the previous episode. And what we have added here is textureDiff. Okay, so this is the function that actually performs the numerical differentiation of a texture in UV space. And we're using the symmetric difference quotient method to estimate the partial derivatives of the texture at the point UV. Okay, and written out mathematically, so we're representing our texture as a function of f UV. I could write that f there. So it's a function f that represents the procedural texture, so we get a value at every point given by u and v. And to calculate the gradient in the u direction, we evaluate f at u plus hv minus f at u minus h v, okay, and then divide that by 2h, where h is some kind of tiny number, some small number that we use. And we do the same for the gradient in the other direction, in the v-axis, where we hold u constant and do v plus h, and we hold u constant and we do v minus h. Okay, so this is standard partial differentiation. Okay, we hold the variable we're not interested in constant and vary the other one. Okay. And that will give us our two gradients, which is the vector that we return. Okay, so to implement that, we simply define h, in this case is 0.001, a nice small number. I mean, that's kind of arbitrary, but it has to be small, but not too small. So I found this value seems to work well. We then initialize vectors for the u displacement and the v displacement, okay, which are initialized as h, 0 and 0h. Okay, that makes sense, I think. And then we simply define our u gradient and we calculate it. We call input texture, so that is the texture that's been passed to the function, and we call the get value function, which doesn't exist yet. We're going to talk about that in a moment. Okay, we're going to add that to the texture classes. So we call the get value and we pass uv chords plus u displacement, okay, which is going to move us 1 unit in h, minus input texture get value at uv chords minus u displacement, right? And divided by 2h. And you can see how that is an implementation of that, I think, quite clearly, okay? And this is why I didn't bother explaining the maths with the slides and things like I normally do, because I think this is quite simple, and oftentimes I find, personally, for me anyway, it's actually easier to understand the maths when I see it in code. So anyway, well, hopefully that will work for you as well. Okay, and we then just do literally exactly the same for the gradient in the v-axis. Okay, we get the uv chords plus, we get the value of the texture at uv chords plus v disp minus the value of the input texture at uv chords minus v disp. Okay, and again divided by 2h. Right. And then we simply form a vector of that output. And I've written a comment here that we negate the gradients of the surface normals. Actually, we don't. Sorry about that. Yeah, so those comments, do you know what? I'm just going to take those out because we're not doing that anymore. Okay, so we form a vector of the output, and yes, there we go. So output is std vector double is u grad times 1 comma v grad times 1. That we don't need multiplied by 1. In fact, the compiler, I imagine, is smart enough to realize that that doesn't do anything useful, and it would have taken that out for us, but we can take that code out. Okay, so there we go. So we simply form an std vector object of type double, initialized with ugrad and vgrad that we calculate here, and then we return the output. Okay, and that is everything that we need for the texture diff function. So just to reiterate, the purpose of this function, it accepts as input a pointer to a texture, procedural texture. It evaluates the gradient of that texture, the two-dimensional gradient of that texture at the point given by uv chords, and then returns that as a two-dimensional vector. Okay, great. Now, that is actually everything that we wanted to change in normalbase.cpp, okay? Okay, so the next class that we want to make some changes to is texture normal, okay? In fact, we don't want to make changes to this. We are creating, this is a new class that we're creating, which is a normal map based on textures. Okay, so as always, we have our include guards, and we bring in normalbase.hpp, and we hash include random. We're not actually using that, to be honest, and that's just left over. We put this in our qbrt namespace and into the normal sub namespace. Okay, I'm not a big fan of nested namespaces, but I think 2, possibly 3 levels is not too bad, and I think in this context it really does make sense. Okay, we declare our class as texture normal that inherits from public normal base. We have our constructor and destructor, as always, texture normal and virtual tilde texture normal to override the destructor. We have a function to compute the perturbation. Okay, that's everything we talked about in the previous episode when we looked at the basic implementation of normal maps. And then we have our assign base texture function, which we're going to simply use to assign the texture to the normal map that we want to create the normal map from. Okay, so that obviously just accepts as input an std shared ptr to a object of type texture base, okay, input texture there, and we declare some public variables. We have a scale which we set to 1, and we have a flag called m_reverse, and we can use this to change the direction of the perturbation based on the gradient. Okay, initially set to false. And we have two private variables. We have m_have_texture, which is a boolean initially set to false. This is simply a flag to say whether we have a texture assigned or not. If there's no texture assigned, we obviously don't want to do anything. And we also then create an STD shared PTR type texture base to store the actual base texture, or to store the reference to the base texture. Okay, right. That is everything for texturenormal.hpp. Let's have a look at texturenormal.cpp. Okay, so this is the CPP file. Pretty standard. We hash include texturenormal.hpp, of course, that we've just talked about. We have our constructor and destructor. We don't need any code in those. And we have a function to assign the base texture. So this is assign base texture, no return type from that, accepts as input an STD shared PTR type texture base, of course, to the input texture. And we simply store that reference into m_p_base texture, and we set the m_have texture flag to true. Okay, and then compute perturbation. This is replicating the code to some extent that we talked about in the previous episode. So it initializes x, y, and z to 0. If we have a texture, then we do stuff. If we don't do anything. So if we have the texture, we compute the UV gradient by calling the texture diff function from the normal base class, okay, that we've just talked about. We're passing the reference to the base texture and UV chords, okay, which are input to the compute perturbation method. If reverse is not set, then we simply set, if reverse is false, then we set the x and y values to be minus the first element of UV grad multiplied by the scale, and y to be minus the second element of UV grad multiplied by the scale. Otherwise, we set them to the positive values, okay? It's pretty straightforward, and we then create a vector called perturbation that we initialize with values x, y, and z, and then we simply return the result of perturbed normal passing the original normal and the perturbation. Okay, and that's it. That's pretty straightforward. That really is the code that we need to implement texture-based normal maps, and as you've seen, it's a very powerful technique. That comes from really a very simple method. Okay, so we need to make some minor changes to the texture classes that we've already developed in order to make this work. You will notice that I used a getValue function, and the original implementation of texture base and the resulting classes that inherit from that did not have a getValue function. So we're going to add that now. So if we look in texturebase.hpp, we have the prototype for getValue. Okay, it's pretty much the same as getColor, except it returns a double. So this is virtual because we're going to be inheriting from it, or we're going to be overriding it rather in our inherited classes. It returns a double, that's called getValue, and it accepts as input simply a constant reference to the UV coordinates. Okay. And that's it. And it returns the actual texture value. If you remember back to the episodes where we talked about procedural textures, the first thing that we do when we calculate a texture is we generate a value between 0 and 1. And then to actually create the pattern that we see on the screen, we use that value between 0 and 1 with a particular color map in order to compute the color of the pixel. That's not what we want. What we want to, when we come to compute the texture gradient, is we want the original value between 0 and 1 rather than the color that has been arbitrarily decided by whatever color map we've assigned. Okay, so that's what we're interested in. That's why we have to add this additional method or function. Okay, let's have a look at texturebase.cpp. Okay, texturebase.cpp, that's nothing much has changed except we have now the declaration here of getValue, which is exactly what you'd expect. This is the base class, so it doesn't do anything. It simply returns a default value of 0. Okay, really very straightforward. Okay, so I just want to show a quick example of how we implement the getValue method. I'm not in this video going to go through every texture class and make the modifications. Okay, I'm just going to show for the gradient, the very simple gradient texture, and the process is the same. If you want to go through and modify them yourself, just follow the same pattern. So if we look at gradient.hpp, the first thing that we obviously do is add a virtual reference to the getValue function, which we're overriding. Okay, so it comes from the base class, right? And let's look at gradient.cpp. Okay, gradient.cpp, and here is the code for getValue. Now, this is the original code that we had here that actually computes the color of the procedural texture at the point given by UV chords. Okay, so the first thing it does is it applies any local transform to give new location, and then it simply calculates the value, okay, using this here. It's simply a gradient in the U direction, so it's really very straightforward. And then it returns the value derived from the color map class. Okay, so the gradient texture has an internal color map class, and it calls the getColor method of that class with u. So u is the value that varies between 0 and 1, and then that is used to return the color. But to calculate the gradient of the texture, we want the value that varies between 0 and 1, i.e. this value of nu u. Okay, so we want everything except up to we want all of this code, but not this code. So what I've done is simply copied and pasted that code into the getValue method. Now, of course, the more diligent of you will spot that that is terribly inefficient because I've duplicated that, and what I could do is simply delete this code from here in getColor and replace it with a call to getValue. And indeed, I will do that, but simply for illustrative purposes, I've left it like this. So the new getValue function, which is here, simply has exactly the same code, and except rather than returning the color from the color map, it simply returns the value given by this. Okay, that will be a value between 0 and 1, and then we can use that in the texture diff function that we've just talked about to actually calculate the texture gradient. Okay, cool. That is basically it. Now, because the stone, as I've called it, procedural texture that we've seen in the demonstration there just looks so good, I just want to talk about that, and I've included that class now into the repository as well. So let's take a look at that now. Okay, so this is qbstone1.hpp. This is a specific stone class, or stone pattern texture class that I've created. It goes into the texture namespace, the texture sub namespace of the QBRT namespace. It's called qbstone1, inherits from texture base. This is it's just a standard header file for texture. So if we look at these specific things, so these functions, those are all standard and we've talked about before. Okay. We have a pointer to store our color map. Okay, so an std shared PTR that stores our color map. We have a flag to say whether we have a color map or not. We initialize, or we need 2 noise generator instances. Okay, so again, if you don't know what that means, go back and look at the episode on procedural textures where I talked about the specific episodes where I talked about procedural noise. Okay. Value noise or gradient noise. Okay, so in this instance we're actually using value noise. So this is the value noise generator. We create 2 noise generator instances. We have 2 amplitudes, 1 and 2, which we set to 8 and 4 respectively, 2 scales which we set to 6 and 30 respectively, and then we have 2 variables to store the minimum and maximum values. That is everything we need in the header file. Let's have a look at qbstone1.cpp. Right, here we are, qbstone1.cpp. So in the constructor here, because this is a specific procedural texture, rather than making this all configurable for, where from the point in the code where we actually create an instance of it, I've hard-coded the pattern because it is a specific pattern. So we set up our initial configuration in the constructor. We set the amplitudes both to 1, scales to 32 and 64 respectively, and the min value and max value to -2 and +2 respectively. We configure the noise generator simply by calling their setup grid function and passing the scale. So the relevant scale, noise generator 1 is m_scale 1, noise generator 2 is m_scale 2. Okay, and then we configure the color map that I've called stone map. It's an instance, as we use std make shared to make a shared pointer to a color map instance, which we then create, and then we've simply set the stops of that 2, 3, 4, 5 stops between 0 and 1, and these respective colors, which are, as you can see, all just different shades of gray. And then we set the color map to stone map. So the set color map is a function of this class, and we use that to simply set the stone map. Okay, we have nothing in the destructor because we're not using raw pointers or naked pointers, so we don't need to worry about that, which is really cool. And then the getColor method, this is pretty standard. Okay, so we have our initial block of code here that applies any local transform that might be applied. I've talked about that before in procedural textures. And then if we don't have a color map, we simply return purple, which is a good indication in the scene if something's wrong. Otherwise, if we do have the color map, we calculate the base function. So we simply get the value from the first noise generator at u and v multiplied by the first amplitude, and add to that the value of the second noise generator at u and v multiplied by the second amplitude, and then we calculate map position, which would be a value between 0 and 1 based on that noise, and then we simply return the color from the color map. Okay, pretty straightforward. And exactly as before, the getValue function is exactly the same code. And again, I've done it this way because I feel it's more illustrative. We could, of course, replace a lot of this code up here with a call to get value. That would be more efficient. But anyway, it doesn't matter. So this is basically the same, except it returns map position rather than local color. Otherwise, it's the same. Okay. We then have a function to set the color map. Okay, it's pretty conventional, just stores the color map and sets the flag to true. We have a function to set the amplitude, which, interestingly, only sets amplitude 1. Anyway, it doesn't matter because they're fixed in the constructor anyway. And then a function to set the scale again. Okay, but we're not going to worry about that because they are set in the constructor. Okay, that is actually everything for the QBStone class. So lastly, before we can see a demonstration of what this actually looks like, we just need to modify the scene class so that we can actually produce a result. Okay, so let's look at that now. So firstly, in scene.hpp, the only thing we have to do here is hash include texture normal, the new class that we've created from the QBNormal subdirectory. Okay, we have no other code there to change, that's it. And let's look at scene.cpp. Okay, scene.cpp, very simple. We don't make any alterations to the camera, the base lighting, or the color maps. The only thing we do here now that's different is we set up an instance of the stone texture. So we have stone texture is equal to std make shared type QBStone1, initializing with QBStone1. And then I have set a transform because yeah, I just wanted to scale it. So the only thing we do is we set a transform where we set the scaling to in U and V to 4, both of them to 4, okay? And blah, blah, blah. Everything else there is the same as value noise, the marble, cloud, spiral, and the wood that we see on the spheres. And then we create our simple normal map. So we're simply creating normal map as an instance of texture normal now. That's the new class that we've talked about today, the class that creates normal maps based on an input texture. We call the assign base texture function of our normal map to assign to it the stone texture that we've created up here. Okay, and we just set the scale to 0.015. That's a value you can play around with to change how it looks. Okay, and then really all we've done in floor material, we assign texture to floor texture and floor material to norm map. Okay, yep. Okay, no, we don't use floor material, scratch that. So the stone material here, we just create a material for it called stone mat, created with an instance of the simple material class, which we set the base color to white, the reflectivity to 0.35, shininess to 32. We assign the texture, stone texture that we've just talked about, and we assign the normal map, okay, that we've also just talked about. And then where we create the actual objects, we create our spheres and we create our floor. The only thing now that's different is floor. Here we have assigned material, we pass to it, we assign the stone material to it instead of the floor material that we had before. And that is everything. That is everything we need to change to our scene. So let's go back to our terminal window. Let's compile this and let's see what happens. Okay, so here I am at my terminal window. I'm using gmake to manage my builds. So I'm just going to run make and let that run through and do that. If you're doing this in some other integrated development environment or something, compile the code in whatever way your IDE uses. Just let this run through, compile everything. I have tested this, so there should be no errors, hopefully. And there we go. Okay, so let's just run our code, such QBRay, and let's see what we get. So as I've said before, it's not the fastest ray tracer in the world, but that is something we will look at addressing in future episodes. There are various ways, actually, we can go about improving performance, but we'll not worry about that for the moment. There we go. So that is the result that we can get. And I think that's really quite a nice demonstration. So we have the 5 balls here as before with the different textures on, but now we have this kind of winkly, wavy sort of looking pattern going on the floor underneath them. And you can see the reflections and the shadows exactly what is working. And I think that's quite a nice demonstration of what texture-based normal maps can do. And I mean, this is exactly the kind of thing that I wanted, so I can create interesting procedural textures. And now using the texture normal class, it's then really simple to make a normal map that goes with that texture, and it just makes really interesting results. I mean, it's not necessarily reflective of anything actually in the natural world because, you know, it's just based on the texture, but it looks nice. And sometimes that's really what it's about, isn't it? You just want to make something that looks good. It doesn't have to be necessarily an accurate simulation of physical reality, just something that looks good. And I think that's what we've got here. Okay. Yeah, so you can play around with the amplitude of that and various things, or look at applying it to different textures, and you can create all sorts of really quite interesting effects with that. Okay, so I mean, that's everything that I wanted to talk about today for texture-based normal maps. I've got one more episode to do in this mini-series looking at normal maps, and that is to work with to look at how to work with image-based normal maps. So if you look at any of the websites that allow you to download freely available PBR textures and that sort of thing, they usually come with a whole series of different images representing the different aspects of sort of diffuse colors and all sorts of various things. But there will always be, or usually will always be, a normal map associated with that, which is usually a kind of purpley, bluey kind of looking image that represents how the normals of the surface should be perturbed, and that adds surface detail in exactly the way that we've been looking at today. So the next episode, that is what I'm going to focus on. I'm going to focus on how those images work and how we can go about implementing those in the code, which will hopefully be of interest. Anyway, I really hope this video today has been of interest. I really hope you've enjoyed it and found it useful. Please do let me know what you think in the comments below. And yeah, like I say, if you enjoyed the video, please do hit that like button. And if you haven't done so already, please consider subscribing to my channel so you don't have to miss any future videos. Thank you very much. Right, that's enough for me for today. So like I say, I hope you've enjoyed it. I had a great deal of pleasure making it. And yeah, I really look forward to seeing you in the next episode. Thank you very much for watching. Bye.